All right, let's get right into it. Today we're looking at one of the biggest, most critical challenges that wildlife faces all over the world: habitat fragmentation. Now, it's a huge, complicated problem, but the good news is scientists have come up with some really powerful theories that help us make sense of it and maybe even start to fix it. Okay, let's dive in.
It all really starts with a simple question, something you've probably seen 100 times without even thinking about it. What actually happens when a single road, just one, cuts right through a huge forest? It might not look like much, but that one simple line on a map, it literally changes everything for the animals that live there.
And make no mistake, the stakes are incredibly high. That simple road is part of a massive global process. And we now know that this habitat fragmentation is one of the main reasons we're losing species and biodiversity all around the globe. This isn't just about losing a few trees. It's about systematically pulling apart the fabric of entire ecosystems.
So, to really get our heads around this, we're going to start by looking at what it actually means to live in a world that's been broken into pieces.
So here's the formal definition. Habitat fragmentation is simply the process where a big, continuous habitat gets chopped up into smaller, more isolated patches. And that word, isolated, is absolutely key. See, it's not just that the total amount of forest gets smaller, it's that what's left behind is disconnected, creating these little islands of nature in a big sea of human development.
And this whole process has three really big impacts. First, and this one's pretty obvious, it just reduces the total amount of space that wildlife has to live. Second, and this is so important, it isolates the populations that are stuck in those little patches. And third, it creates this thing that scientists call the edge effect. Basically, the borders of these new fragments get blasted with more sunlight, more wind, and different temperatures, which can totally change the environment and make it unlivable for species that rely on that deep, dark forest interior.
So, how in the world do we start to predict what's going to happen to all the species living in these new isolated patches? Well, it turns out the first big clue didn't come from studying forests at all. It came from looking at actual islands out in the middle of the ocean.
So, way back in 1967, two biologists, MacArthur and Wilson, came up with something called the theory of island biogeography. They figured out that the number of species you find on any island isn't just a random number. It's actually a constant dynamic balance, a kind of tug of war between two forces: new species arriving from the mainland and species that are already there going extinct.
And this theory leads to some really clear predictions. A big island that's close to the mainland, well, that's going to have the most species. It's an easy target for newcomers to find, and it's large enough to support healthy populations. But what about a small island, way out in the middle of nowhere? It's going to have the fewest species, because it's just harder for animals to get there, and the limited space means populations are more likely to die out.
So yeah, it all really boils down to these four things. The physical stuff, how big the island is and how far away it is, those directly control the biological stuff, the rate at which new species arrive and the rate at which they disappear. It's this beautiful, elegant dance between these factors that decides how much life an island can actually support.
And this right here, this was the huge aha moment for conservationists. They suddenly realized that these patches of forest, these fragments, were behaving just like islands. The mainland was whatever large, intact forest was left, and the sea was the roads, the farms, and the cities all around them. All of a sudden, they had a powerful new way to understand what was happening.
Now, the island model was a total game changer for sure, but it had one limitation. It mostly looked at each patch all by itself. Science pretty quickly realized that to see the whole picture, you had to stop seeing these as lonely islands and start seeing them as a potential network of survivors.
And this led to a really important evolution in our thinking. So while island biogeography kind of zooms in on one patch and its connection to a big mainland source, metapopulation theory zooms out. It looks at the whole system of patches as a network, where any patch can be a source for any other patch. The key idea isn't just one-way emigration anymore. It's this dynamic cycle of extinction and, this is the magic word, recolonization.
This whole idea was pioneered by a guy named Richard Levins. A metapopulation is, well, it's basically a population of populations. You've got this whole network of smaller, local groups, but they're connected because animals can actually move between them. And here's why that's so powerful. The entire system can survive for the long haul, even if some of those individual local populations wink out of existence for a while.
It all happens through this constant rescue cycle. So picture this. A population in one patch goes extinct, maybe because of a fire or a disease. If that patch were totally alone, that's it, game over. But in a metapopulation, individuals from a healthy patch next door can just wander over and recolonize that empty habitat. It's this incredible dance of disappearance and rescue.
Which brings us to what is honestly the most hopeful part of this whole story. Because once we understand the science of networks and connections, we can actually start designing solutions in the real world. We can literally start connecting the fragments back together.
And the number one tool we use to do this is something called an ecological corridor. You can just think of them as wildlife highways or maybe habitat bridges. They're these strips of land that create a safe physical connection between two or more of those isolated islands, giving animals a path to move back and forth. It's meta-population theory made real.
Let's look at a perfect real-world example. In the Cantabrian Mountains in Spain, the brown bear population had been split into two totally separate isolated groups because of roads and development. And this was a huge problem. It meant there was no gene flow between them, which is terrible for genetic health, and it meant both of these small populations were at a much, much higher risk of just disappearing forever. So what did they do? Well, they applied the exact science we've been talking about. First, they mapped out the key habitat patches. Those are the islands. Then they studied how bears move to figure out the most likely routes they would take. And then they worked to protect and restore those areas, creating ecological corridors to link the two populations back together. The goal was pretty simple: turn two small vulnerable groups into one big resilient metapopulation. And this incredible case study brings us right to our final section, which is all about taking these lessons and using them to design conservation plans everywhere. We're no longer just protecting spots on a map, we are actively designing for survival across a connected landscape.
What this science really tells us is that we have to fundamentally shift how we think about conservation. We can't just draw a box on a map, call it a national park, and then just hope for the best. We have to think like a meta-population. That means designing our protected areas as an interconnected network, making these corridors a top priority, and managing the whole system as one dynamic entity that can adapt to whatever changes come its way.
And if there's one thing to take away from all of this, it's this right here. The goal of modern conservation isn't just about protecting individual places anymore. It's evolved. The new goal is to protect the connections between those places, because we now know that the survival of a species doesn't depend on the health of just one patch. It depends on the health of the entire network. Which, of course, leaves us with a really tough final thought. Now that we know just how critical this connectivity is, how do we make those hard choices on the ground? Should creating these vital ecological corridors be prioritized over building a new highway or a new housing development? This is really the central challenge of conservation today, trying to find that balance between the needs of a connected planet for wildlife and the undeniable needs of our own human society. Thanks so much for joining me.